Okay, so in this video we're going to look at the wings, or the various wing types. Now we're not going to cure all the wings actually in this one, just because some of them are attached to things like control surfaces and we don't want to actually touch those, because those will get touched when we actually do control surfaces much later in the process. But let's look at the existing wings, and we'll talk a little bit how to do it. So we can do this by doing T:\wing in the search bar, and that will give you all elements with a wing component. You can see over here we've got a wing component. So you can see these various versions of. I'm not even going to touch the damaged and destroyed ones for now actually. That's largely because I don't want to look at the damaged and destroyed elements as yet. We'll do that again later in the process. This is just to cover how to set up the wings initially. So if we utilise Unity to kind of look at this from the top down, we can see here that currently the wing on the left wing, or wing left aero, is currently sat over here somewhere, and obviously this is because the mirage is significantly tinier. The mirage ends up about this big somewhere. So it's in the wrong place for a starting point. So we can resolve that. Same for wing right aero. So we want to move those two. Now actually, to make this easy, we want to make them move backwards about the same amount. If we highlight them together, I use control there to highlight them both. We can move them backwards down the aircraft, it'll move them both the same amount of distance. So move this backwards to about here. You can see both like that distance. Now arguably, really what we want to do is we want to push those wings out slightly to the sides. So you can see here that the X position there is 0.011111. So let's see if we push it out to the middle. Maybe set it to 0 there, or 0.111. So that would mean that it goes from minus 0.0111 to there. And what I want to do is move the other one the same distance the other way. So we need to add, see it go up, move that out to 0.01. So those now are equidistant along the line of the aircraft. Now if I turn it to the side and just look and make sure that actually those line up over the wings, it's about the right height. There's an argument they're slightly out as it goes. So I highlight them both again, and then so they're slightly underneath the wing. Okay, so now I have both those aero points for the wings, and that's how we actually adjust the wings. The wings aren't related directly to the actual model. If you have a look underneath it here, you can see we actually have wing right part, wing right, and all the bits beneath it, and that wing right aero is underneath the actual wing, where the actual models are, etc. So what allows us to do that? So T-wing, getting back to that. So the question then becomes about how do you work out what lift coefficients and all those things are. Well, there are two things initially that we want to resolve. One is comes down to what the type of aero profile is for the wing. Here you can see I've got it set to fighter wing aero mirage, and this is because you can have different types of profiles for different types of wings. Now I can only think of a small number of wing types that you would probably be that bothered about having different. The Mirage is an example because it's a delta wing. Most aircraft you can utilise the standard ones that come with the game. So if I click on this, you can see that it offers you the various choices, and I would choose fighter wing aero for most aircraft, unless it's a delta wing, in which you could utilise the Mirage ones or a delta wing one. Then it's probably not worth worrying about. Now the question, let's go and do the same on this one just so we remember we've actually done it. So the question is, what's the difference between these things? So here you can see that fighter wing aero has a script, it's an aerodynamic script, and it gives you a lift curve, a drag curve, buffet magnitude, buffet time factor, and a buffet curve. The lift curve on here that you can see is based upon the amount of lift compared to the amount of AOA for that wing. And this is the standard one, so you don't need to read too much about it. If we look at the one for the Mirage, then it actually has a much higher increase initially, and then it levels off completely, flattens off at 30 degrees AOA. So once it gets to 30 degrees AOA, the actual amount of lift that a delta wing gets is limited comparatively. And you're going to ask me, how do I know these things, or how did I work these out? Basically, I spent a fair amount of time going through some of these things to have a look at them. For example, the Mirage wing, you can find some of the information for delta wings, etc., based upon a bunch of information. You're just going to search up on Google. So if you really want to make a delta wing or some other unusual wing, and you want to make it realistic, then do that. However, 90% of aircraft in this game that you'd ever want to make will probably have a standard wing layout, like an F-15 or F-16. All have a standard wing layout in terms of their aerodynamic profile. Like I say, the other one that comes to mind is delta ones, such as a Mirage. So that's the first thing to note about what settings you can put on here. The other thing that you've got on here comes down to lift coefficient, drag coefficient, and lift area. Now, lift coefficient and drag coefficient is a really difficult subject to, once you start trying to find out. You think it would be very easy to go and say, okay, well, what's the numbers for these kind of things? If it was me, I would not touch lift coefficient and drag coefficient in most cases, for most aircraft. It's just probably not worth the effort, in truth. Because most aircraft have a kind of very standardised lift coefficient and drag coefficient from the type of aero profiles. It's usually based upon the aero profile, and most of them are fairly standard and probably not worth worrying about too much. You can do, and if you feel like it's not performing exactly as you expect, you can change these. So I remember changing them for the F-16 and for the later ones, like the I think now for maybe the A10, when I did some testing with people on an early version of the A10. If you know for a fact that the drag coefficients are different, i.e. they're lower or higher, or they have a lower high lift coefficient, you can look into increasing these slightly or decreasing them slightly. Again, I wouldn't probably touch too many of these. Maybe in this case I might consider making a change to those to bring them down slightly to maybe 0.3 for the F-15, and maybe decreasing this slightly to like 0.12. So the question then becomes around that other one, which is lift area. And lift area actually is not related to the actual size of the wing directly. In fairness, it is related to that, but it's not the only factor. There are two factors really in how big that number should be, and it's actually called the lifting area in terms of aerodynamics, and you can find other information about this elsewhere. So, but what I'm going to tell you is I'm going to give you the formula that you need for this, and I'll bring it up on the screen in a minute, and then I can explain to you what this means. So, the actual formula for working out the size of lifting area is wing area multiplied by cosine of wing sweep angle to the power of 2, and you multiply that all by a half. So the question becomes, how do you find this information out, I suppose? So I'm going to show you a tool I utilise to find wing area for a start. So here we have a tool called sketchandcalc.com, and this allows you to actually work some of these things out. Now you can do it manually. If you want to do it manually, you're just going to have to work out how big your size of wing is, and then what the sweep angle is. Now some of these things you can find out off the internet, but we'll go through it on utilising this, and then we'll work it from there. So if I use snipping tool, nope, don't want to do that yet. Create no, game object, actually it's 3D cube. Now the 3D cube I created there is largely to show how big a 1 meter by 1 meter is. So if I now do a snip, I do this, I come to my here and do control paste. See, image is loaded. Utilize this little tape measure that tells that I can tell this then that this to there is 1 meter. I click add to canvas. So now what I can do is I can draw around the wing shape. So I click on here, drag it out to there, down to here, and you can see down this bottom right here it tells me how big the area is, how big the perimeter is. So it's telling me that 12.79 meters squared is approximately the size of that wing area. Okay, so we come back to our figures here. 12.79 multiplied by cosine of wing sweep angle. So wing sweep angle is actually not this bit, but the outside bit to 90. Now what I can do is I can zoom in on here. And you can see it says 44 degrees here is that angle in here. So 44 degrees, so 90 minus 44 degrees to the power of 2, then multiply it by 0.5. So the figures for that actually come out at, let's have a look. So put in 90 minus 44 equals 46. Do cos of 46. That's not right. Cos of 46 is 0.75. We then need to square that. It's 0.562. So that equals 12.79 multiplied by 0.52 or 0.5626 multiplied by 0.5, and that would equal 3.598, and that's a figure I want to put in here. .598. So that figure goes in here. And it's as simple as that in that way. So I guess the question is, how does this work out for something like a sweep wing, for example? And what you often find with sweep wing examples is that they actually have big wings, but because they've got such a high sweep back, you end up with having to compensate for that, and that's what you end up with. So for example, mirage wings usually have about a sweep angle of about 55. And if we go into trigonometry and do cos of 55, you can see actually its lifting size is much smaller in there. So that is how you work out what the lifting size is of a wing. You need to know how big the actual wing area is on there, what the wing sweep angle is, in this case 90 minus that there, so it's that bit in there, which in this case is 46 degrees, and then you need to square that and then multiply it by half, and that gives you your wing lifting area. Okay, so that's pretty simple. We can do that for every one of these if we wanted to. So we've got the wing left arrow, wing right arrow. Now here we've got right canard and left canard as well as it goes. Now these actually, on this particular one, are slightly different in the sense that on the Mirage, the right canard and left canard are actually not based on being real canards, they're actually little lifting surfaces. And they actually have a slightly unusual design in order to improve that. So we will ignore those two anyway, because we don't really have those on the F-15. The canards we have here are actually moving surface canards, so therefore they will need to be built into the moving surface. So I'm going to remove those. The other things you can see on here that actually have wings assigned to them, such as the left vertical stable aero, left elevon, etc. So let's go through these a little bit. Body lift aero usually has a very small lifting amount for a bigger lifting area, and whether you include this or not depends upon the kind of aircraft. I would argue in the F-15 actually it probably has some, but not probably as big as what's on here. And the actual amount of lifting coefficient is probably smaller. So I'm going to make this slightly decreased. The lifting area is usually kind of this lower period in between the wings. Clear that, delete that layer. That's given 19.21 meters squared, but remember there is no wing as such here, so there's no way for it to generate direct lift, so that's why you end up with such a smaller amount. Even though it's coming directly into the wind, it doesn't actually have a wing lifting surface, so I found that setting it to about a low lift coefficient, about 2 is about right for most body shapes and sizes. In terms of the other elements you have on here, the ailerons, the two ailerons, the elevons, and you might want to swap those for flaps when we go to the F-15, and then we've got the left vertical stabiliser and the rudder. So the question here comes down to a little bit of, we now have the rudder, which is actually a control surface if we don't want to touch it. We need to look at doing control surfaces separately. But we do have the issue that currently we only have one vertical stabiliser. You can see it's here, actually in the middle. It's at the wrong place, so therefore what we need to look at is actually having two of those. So you can see vertical stab, left vertical stabiliser arrow. So we need to duplicate that. We need to move them. So I'm going to duplicate it first. Duplicate. call it right. And then if we look at it from above, move it across, move it backwards. .3. Say 3. That's 33.2. Let's match up with that side. So now we have two vertical stabilisers. Now what we're going to do is have a look at how big those are. Let's do my cube, bring that up. There's my cube. I'll use that because it's easy to see in the picture how big one square is. Clear all. Manage that as 1. That's the canvas. Down here it's measuring at 4.7 meters squared. And the outside angle is going to be about 36 degrees. So clear all that. 36 cos squared is 0.712. .7 multiplied by 0.713 multiplied by 0.5 gives you about 1.67 lifting area. I think I'll leave these at this. Should be fine. There we go. Now we've created the base wings for our aircraft. Here are roughly the right positions. Things like the canards, as I mentioned, the flaps and the ailerons will all get added later. We'll add the control surface in for the tail as well later, and we utilise when we're going to start doing control surfaces. It's okay, that's edited the actual wings into place.